Hello everyone. Thank you for joining London AI Technology Meetup. So every month we are bringing really interesting topics in this AI Meetup. Last month we had about reinforcement learning. So this month we are bringing on Azure ML and Federated Learning. So we have Alexander Muller joining with us from US about discussing his experience and about the topic. It'll be really interesting area that we are going to discuss today's meetup. So every month we are bringing a lot of new startups, innovative topics and research point of view and product development and technology point of view in this meetup. So keep tuned in every month to this London AI Technology Meetup. So let's get started. So the first part of the session, we are going to discuss about the Azure ML. So I'll be covering about that. Then Mr. Alexander will be covering about the federated learning after my session. So I'll start about Azure ML. So Azure ML is all about cloud ML technology. I think most of you have heard about Microsoft Cloud Platform, which is the Azure platform. So in that, we have this Azure ML platform, which is providing a lot of ML capabilities for the customers. So you can use built-in tools and you can use predefined tool, or you can use SDKs and frameworks. So let's look at further. So you can see in a typical data science project, we need to go through several steps in order to complete the project, right? So we need to gather the data. That's one of the key part. So the data source can come from different areas, right? So that's where Azure provide data inputs like data warehouse, different data sources. Even we can use NoSQL databases, SQL databases, different data lakes, different data services are there. So once we gather enough data, then we can use the Azure ML service, which is providing end-to-end capabilities to create your data science project. So where we can select from predefined ML frameworks, predefined ML SDKs, and also we can use things like hyperparameter tuning in order to configure it further. Then there's a data pipeline we can set up how you can optimize your machine learning algorithm. And we can automate this process as well. So there's a technique called MLOps, machine learning operation, where we can automate because we know we need to retrain and we need to update with the changes that's coming in. So we can do this using MLOps. So Azure ML provide end-to-end capability for end customers or developers to integrate this and finally to deploy it. So then they can create their Flash project, they can deploy it and they can get the end result from that. And also they can automate this process. Otherwise, we need to manually do this. It will take a lot of time. So we can automate this using automated script and MLOps to enhance it further. So you can see there are various kind of services Azure providing. So the Azure ML providing different set of frameworks, the data science tools, and also the built-in tools as well. For example, if you look at the first one, these are pre-trained models. So the first part is pre-trained models. That means you don't need to create any model. Automatically, everything will be there. You just consume the API. So there are vision, speech, language, and search. Pre-trained models are there. But as a data scientist, we know we need to collect the data and we need to prepare the algorithms and we need to finalize and we need to get the right result. So that's why we can use the data science tools like Jupyter Notebook, PyCharm, and these softwares in this. And also it supports the popular frameworks like PyTorch, TensorFlow, Scikit-learn, all the open source frameworks. And also the services that they are providing is the Azure Databricks. Databricks is a software. Then Azure Machine Learning, that is we are highlighting in this, and the machine learning VMs. Because in order to train this, we need to what we need to do is we need to train. Like we need to have computing power, especially the chips like NVIDIA chips are really important to train our machine learning models, right? So the Azure providing these VMs, virtual machines, that containing NVIDIA chips, GPU chips. So where we can do our training process much more efficiently in a shorter amount of time. So it will providing a powerful hardware If you need the Azure in terms of hardware capability, we can use for GPU or FPGA kind of performance, the high performance. So let's say you want to train a video stream, video data with 1 year of video data. We need to analyze and make a putting into a neural network. So that training take a lot of time and it take a lot of computation power. So we can make that more optimized using a high performance kind of computing that is provided with the Azure environment. So you can see there are several set of services that is providing, and they are separating these services for data scientists, data engineers, and data analysts. So in this, we focus mostly the data scientist related services, and also there are some services that provided for data engineers as well. So Azure Databricks is a software that we can process big data, and we can set up clusters and things like that. Then using Azure Machine Learning, we can analyze this and we can come up with the machine learning model. So we can have several options to finalize and fine tune these machine learning models. Then as I mentioned, we can use the machine learning VMs, virtual machines, in order to optimize and in order to increase the performance. So this is the DSVM, Azure Data Science Virtual Machine, where it containing the development tools, platforms already built in. So you just within 1 minute, you get this machine. You can initiate this in the Azure portal, and we can start processing our data model. So it's already, we have all the tools installed in this VM, and it is a really high-end computer with the NVIDIA GPU set. You can select a couple of various options when you are running this machine. So you need to pay for its usage. You pay for 1 hour. Let's say I want this for 1 week, not more than that. So you only pay for 1 week of this machine. So that is more flexibility that's providing in cloud platform. Any cloud platform have similar offerings like that. In this particular session, we focus the Microsoft Azure cloud offering. So where they pay for usage. So let's say a training I need only for 1 week. So I can get this virtual machine only for 1 week. Then they provide the training, the infrastructure. So we can create more advanced clusters. We can use scheduled jobs. We can automate the tasks, things like that. So those more advanced infrastructure kind of a setup we can do. So the Azure network itself, and there are network services that is providing with those kind of support. And the last part here is the Devworks. So Devworks is, as I mentioned, really important nowadays to automate the process. Otherwise, let's say there's a change in the input requirement of data, or new set of feature comes in. Every time we need to manually redo the training. But if you set up Devworks process, it's automatically going through this the steps, and automatically it will update the model. So the model retraining will be automated. We can automatically do this in an automated process. So we call this as ML ops, machine learning ops, because Devworks mostly focusing on software development side. So in the machine learning side, we call as ML ops. So Azure supporting ML ops with this model retraining and requirement, how we can create a version 2.0, version 3.0 like that. So you can see we can prepare, we can build, train, register, and build the image and deploy and monitor. Because once you deploy, we need to monitor this performance and those things. So Azure ML providing these monitoring capabilities of the model, where we can do several set of monitoring and how we can look at the performance and things like that. So those things also helpful for data scientists to look at overall picture, right? So because it's an end-to-end kind of a process, and it's never ending process, right? So once you complete the model, deploy it, it's not going to end from there. So we need to look at it, we need to monitor it, and we need to update it with the changes that's happening in the other environment, right? So you can see the cycle like this, as I shown here. So it's an automated cycle that keep continuing every day based on the changes of the environment or changes like that. So if you set up an automated process using MLOps, this task will be much more easier, and we can automatically set up that. So Azure ML providing these capabilities for you to set up that. So you can see we can use initially for prepare the data, then we can use for the training and building the model, and finally deploying and predict. So this process providing end-to-end tool using Azure ML toolset. They are providing these capabilities where we can choose for multiple options. So it's not like only one option you have multiple options. You can select different options as your toolset, and you can develop from that point onward. So as I mentioned, it supports a lot of popular frameworks, and also framework like Onyx is supporting, where it's an open framework. It's have interoperability to connect with a lot of other technologies. At the moment, it's an open initiative for Microsoft and other global tech vendors. So we can create Onyx model, and we can export it other frameworks as well. So we can create, and it supports a lot of these standard open source frameworks, and we can connect with Onyx model, and also we have a native support with Azure VM, Azure Machine Learning Service, like that. So in the Azure Machine Learning Service, there's SDK. You can try. It's enabled with the PIP package installer, or there's a drag and drop environment for beginners that they can try on. They can use this environment to practice these services as well, right? So you can see we can even deploy this model at scale. So if you want to scale it, let's say we are consuming for more millions of users this thing. So that is also possible. There are technologies like Docker and Kubernetes. So we are using these kind of the containerization. We can scale it, and we can automate it further in today's application. In today's application, it's a enterprise level application where we need to serve millions of users. So where we can enhance it further, and we can automate it as well as scale it. So scale up or scale down based on the requirement. So Azure ML provide these capabilities as well. For example, the image, the containerization is another set of services from the Azure platforms like Kubernetes and Docker kind of a container registry, where we can further use for scaling these platforms. Okay. So let me quickly show up a demo of the platform. So you can navigate to ml.azure.com. So you need to have Azure subscription to get this, and you can get a free subscription by go to Azure, search as Azure free. You will get 200 USD free Azure account just by putting your credit card. So here you can see we have multiple options, like we have notebooks, we have automated ML, and a designer. So like if you want to go with a Jupyter notebook, the option is there. Then there's automated ML. As I mentioned, it's a beginner friendly, where automatically the framework will choose what is the best fit algorithm or mode for your application, for your data set. And then there's a designer that is for mostly for beginner friendly kind of a users. There's a designer where you can drag and drop, and we can get these kind of the processors set up here. So this is mostly for beginner friendly users that we can have, but for advanced users, they can use a Jupyter notebook, and they can import these certain frameworks. And then here you can see we can get the data sets. We can connect from different sources, and here we can set up experiments. So here you can see we can set up a pipeline, or we can set up as a notebook. So once we set up a pipeline, we can even set up like different environments. You can see these are like CUDA is, the NVIDIA CUDA platform is really popular, and we want to do high-end kind of data training in terms of video and audio. That is possible. Then you can even connect with APIs, endpoints, and things like that. So it's an end-to-end kind of a support platform that we have. So everything together we can automate, we can scale. Even if you're building a POC, we can use this platform to build. It's an end-to-end kind of a solution. So you don't need to connect multiple tools. You have everything in one platform using Azure Machine Learning tools environment. Let me also share this reference in the chat. You can take a look at it later. I will share in the group as well. Right. Okay. So in this, you can see where we can automate, and here we can set up a compute cluster. What kind of compute you need? You can select GPU. So you can see there's a NVIDIA Tesla P100, NVIDIA Tesla GPUs, right? Like that, you can select what's the GPU, what you need. So likewise, there are a lot of options that we can select. Based on that, we can configure it based on our data set, and we can automate it, and we can make the most out of it using this platform. So that is, you can read more about this URL I shared, and we plan to do more like a hands-on session later, how to use a step-by-step kind of process. This is more high-level kind of a discussion about this Azure ML platform. So similarly, other cloud providers also providing similar kind of platforms and capabilities to make more kind of automated kind of a process. So the teams can collaborate and they can build more end-to-end kind of a application. So if you have any questions, we can have like a 1 minute before going into the next part of the meetup. Otherwise, we have a common Q&A during the end of the session as well. Just if you have any questions, just let me know in the chat, or you can ask, unmute and ask. Any questions so far? Right. So the main key point is Azure ML providing end-to-end support with the Microsoft capabilities, and also for data scientists and data engineers can work together, and also the DevOps engineers can work together to build end-to-end solution, and you can scale it, scale up, scale down, and you only pay for the usage. So that's a lot of like this kind of flexibility is there if you're using Azure platform. And also the other cloud providers also providing a similar capability like AWS, Google Cloud, other cloud, IBM. So they also have this AI platform with them. So they also provide similar capabilities, but based on the project you are involved on, it will be different from one platform provider to another platform provider. Okay, so any other question you can point to at the end of the session as well. So we'll move to the next part. Our guest speaker, Mr. Alexander Muller, will be sharing about private AI via federated learning. It will be a really interesting session. So I will give him next to open up and share about the topic. Thank you.
Yeah, thanks a lot. Could you enable screen sharing for me, please?
Yeah, of course.
I have this conversation with a coworker every day where I'm the guy forgetting that I need to enable screen sharing. All right, can everybody see my slides okay? Please kick and scream if you can't see or hear me.
Yeah, of course, we can see.
Real quick, who is this guy and what qualifies him to be here talking to me about this topic? Here goes. You know, I'm from St. Louis, Missouri. That's kind of Chicago's ugly little brother. I'm like a math guy by education. I did a doctoral degree at the University of Michigan. I worked in data science heavily in healthcare for a long time. Healthcare probably all over the world is very privacy conscious data. Those experiences, both my math background and working in a very privacy conscious vein of data science, got me really interested in emerging privacy tech, and I founded a company called Capion Incorporated. I'll try to spend a tasteful amount of time talking about exactly what my involvement in these things is. I made the slides available on GitHub. There's a link on the meetup page, as well as I put one in the Zoom chat. So if you want to follow along, there's also some links in the deck you might want to look at later. You should check that out. Okay, here's an agenda for the talk. What are we going to talk about? So first, very high level, I'm going to talk about informally, well, what is federated learning? And the idea is that it's a big headache for human institutional reasons to get a bunch of data from a bunch of different people and pile it up in one place to do your project. And federated learning is a way to send code to the data and not data to the code. And there's a lot of business regulatory compliance kind of benefits to doing this. And it's really cool and high tech. And if you're a math nerd like me, you'll think it's really cool. I'm going to go into just a very kind of stylized fake example. I probably have some United States-centric biases I tried to get rid of, and I probably didn't do a very good job, and I'm sorry in advance, but I hope the storytelling survives. And then I'll talk about a couple important subcategories of federated learning that I think are both illuminating, and then you may run into these words if you research the topic later yourself. I'm going to go into some detail. I've called it what federated learning isn't, and in particular, it overlaps a lot with some other emerging privacy tech you might have heard about. And it's in an important way, it's not a new model. It's a way of training your favorite old type of model, whatever it might be, in a way that you don't have to pull up all the data in one place and pick up the risk that comes with it. I'll go into a little detail, just a basic example of how would you do something like this for linear or logistic regression? That's kind of step one of modeling. Finally, I'll talk about some practical matters. I'll refer you guys to some software tools for doing these things. I'll talk about what are the performance concerns that come with doing things in this way. It's not free. And I'll close by talking a little bit about the business value. Why do I want to bother to do this? I think if you're like a tech person, you'll think it's cool. I have been tortured by being somebody who thinks things cool, and then I get to explain to business people, why is this worth your time? And I'll try to give you guys that story at the end. Okay, I'm also going to bully the audience. Are you guys alive out there? Does this make sense? Can anybody make a sound? Alex, you've been cursed by sharing a name with me. Are you alive? Nope. Okay, somebody call his family. All right, goals. Good. Thank you. That makes me feel better. What is federated learning and why might it be useful to me? So that was very much in the agenda. And then a little bit tougher and maybe not for everybody, I'm going to talk about how does this tool work and how do I start using it? So that's more the details of the linear regression example and the software tools. And it really is, I think, a great concise description is we don't want to send data to code. We want to send code to data because that's more secure and more private. Okay, so here's an example. This is just a silly stylized example. You could be doing a project that requires ideally data from a lot of different sources, or more subtly, you might have been able to do a project, but you were full of despair because you don't think you could get everybody to give you the data. So in the United States, for sure, and I'm guessing some other places as well, people don't like to share healthcare data because it's very sensitive and it's very embarrassing if you lose it. So it could be true that data about you that might be useful for, let's say I was building a model to predict who gets cancer. It's possible that ideally the data to build that model is held by a lot of different organizations. And it can be kind of a nightmare that has nothing to do with data science or machine learning or anything like that. Dealing with all these different actors and getting them to sign off on giving the data and assuaging their different concerns about privacy and security and such and so forth. So the consulting business is at times a great example of this. I have this silly example about a made-up person named Gunther. They're a little company, all these big healthcare entities that I have made up, but you can fill in something real and familiar to you. Do they feel comfortable giving this little company all this data to do this AI project? They might not. And this is an ideal setting for federated learning for reasons I will explain, both because federated learning is going to help with this biz dev process of giving Gunther something to say to these people about why he's going above and beyond to protect their data. And then also this is a very natural, from a technical standpoint, federated learning is about, you have a graph and you're asking questions of the other parties of the graph in a private way, and you don't need to pool up all the data in the middle. So this is kind of an alley-oop. If you run into a problem like this, this is when you want to use federated learning. Okay, so I just want to get some terms out of the way. There's some terms from graph theory that come up in federated learning all the time, and I am probably not going to be able to not accidentally use them, so I'm just going to say what they are. So, you know, a graph, this is an example of a graph. A graph has nodes, which are the circles, and edges, which are the lines. In federated learning, a node is always going to be a data silo. It's somebody that's got an interesting data source that's useful to somebody, but they are very leery about sharing it. There's some kind of relationships among these data silos. They could be parts of one company. They could be different companies. They could be the government of a company. Conceivably, we could share data in some way across these relationships, and those are the edges of the graph. And so going back to code to data, instead of moving data, sharing data and moving it along the edges of the graph, we're going to send instructions about how to do something special with the data that's eventually going to allow us to build a model. So all you really need to get out of this slide is that a node, like I'm going to use this language graph theory, a node is an entity that has data, and we're interested in how these entities that have data are sharing with each other or not sharing with each other. Okay, so I'll stop here for a second. Is everybody tracking me so far on just setting the stage? If you're not, please complain, because you're going to start having even less fun right about here. Is anybody willing to go out on a limb saying they're tracking and having a good time? Nobody, eh?
I'm tracking, but not having a good time.
You're not having a good time. Is there something I can help with?
No, that's fine.
Oh, okay. All right. Okay, so how does this tend to work? Oh, we got a question in the chat. Okay, good. Having a good time. That's what I wanted to hear. How does this tend to work? It's sometimes a little fancier than this, but the rough idea is that there's somebody who's building a model and somebody who has data. And the whole point was that the person that has data didn't really want to give it to the person that has the model. And so roughly how this is going to work, and I'm going to go into more detail later, is instead of asking for the data, I'm going to send the data holder a candidate model. And it could be a really stupid candidate model like y equals 0 all the time. And I have an agreement with that data holder of a particular way that they can give me some instructions about how to make my model better. And I may be having this conversation with a lot of different people holding the data. They're going to give me some instructions about how to make my model better in a way that doesn't reveal a lot of information about their data. So here's a really silly fantasy example. Hungarian food has a lot of the spice paprika in it. I am going to post a review of a Hungarian restaurant I went to. I'm going to say, yeah, too much paprika in everything. This is going to help that restaurant, at least relative to my taste, make better food. That I have revealed that there is paprika in the food is not really giving away the menu of this Hungarian restaurant to its competitors. Every Hungarian restaurant is putting paprika in their food. So the point is, what kind of techniques can you leverage to help refine a model, but not in a way that is giving away the data you used to make those instructions about how to refine the model? And then in practice, what's depicted in this diagram, we're going to do it a zillion times until we have a good model. And once again, good is going to be determined by a carefully made private process of I'm sending this candidate model in a special way to all these people with data, and they're giving me feedback. Hey, that looks pretty good on the data that I can see. All right. And once again, code to data. The code is essentially the instructions I'm sending about testing out information about my model on your data. Okay, if you are reading into this area, if you start reading papers or something like that, an important dichotomy is horizontal versus vertical federated learning. And this is also just illuminating to discuss in general. So in what way is this person, do they have data that I don't already have? And there's roughly two possibilities. It's possible that they just have more observations. So for example, if I was doing something in the healthcare field, they might have just data on more patients, the same information on more patients. If I was training a deep neural net model, it's probably true however much data I had, I wanted to have more observations. So that's horizontal. And then vertical is more information on the observations I already have. So I think it's pretty common in the advertising and marketing technology space right now. I would like to collect information from other websites, other publications about people I'm advertising to. And that information is going to be held by all these other companies. So I'm not getting more people via this process. I am getting more information on the people I was already interested in. These are not exclusive, by the way, although federated learning, it's not super duper easy. So people tend to be focusing on one or the other. I will also say, sometimes you hear the homo-hetero dichotomy applied in federated learning. I am kind of lying here, but homo is basically the horizontal case. That's where everybody has the same schema of the data they're bringing to the table. Hetero is different schema. So it's a slight lie, but that roughly corresponds to this horizontal and vertical. To advance for this talk, a lot of the time when you're doing federated learning, it's a hub and spoke model. There's a modeler getting data from a bunch of people. You can get fancy and have a decentralized peer-to-peer network and try to do federated learning on that. That's quite a bit harder, and I think not really ready for prime time now mostly, but in principle, you can, and at some point I think that will start to become exciting as well. So I'm ending a subsection here. Is everybody tracking all right? Feels comfortable so far with just, the rough idea of federated learning? And maybe these kind of categories about, when we're pooling data, in what way are we pooling it? All right, okay. All right, so there's a number of what are increasingly being lumped together under the term privacy enhancing technology right now. These are about working with data in a private way, not really revealing what's in it. And in general, the story in federated learning is somewhere deep under the hood, we are going to use some of these privacy enhancing technologies when we're passing data around our graph, node to node, the hospital to the modeler, etc. We're going to use one of these techniques. Time willing, I'm going to go into detail about what some of them are. But the idea is we're going to try to start with a minimally revealing object. So I'll talk in a second about gradients are a good example. If that word is not totally, you're like immediate to you, I'll get into detail in a second. Start with a minimally sensitive piece of information, and then you're going to use maybe some extra techniques depending on your goals to protect it even more. And it can depend, and there's a lot of different approaches out there. Federated learning isn't one thing. It's a bunch of different approaches to training things in a private, decentralized way. But the story is vaguely always like this. We're moving around a minimally revealing, useful thing, and then we're going to play extra games, do extra privacy tricks on top of it. All right, absent questions, I'll go into a little bit of detail about how do you do this for linear and logistic regression. It's going to be a little bit mathier. If you don't like that kind of stuff, I'm sorry in advance. Assuming my slides work. Okay. When you do linear regression, multiple regression, a lot of the times, you just tell scikit-learn to do it and it gets spit out. Who cares where it comes from? You can compute the coefficients actually directly, and this is typically what people do. The reality is that those coefficients are what they are because they are the solution to an optimization problem. An optimization problem that somebody else solved for you in the 19th century. And so that optimization problem is, I want to find a linear function of my variable. So something that looks like f of x is theta 0, that's the constant term. And then I have a coefficient for every variable, the theta I. And I want to minimize some kind of loss function. In standard multiple regression, that's the mean squared errors. And that's just taking every observation, what did I predict, and then what actually happened, and how far apart were they, and then for technical reasons and statistics, you really want the square of this. At the end of the day, the point here is that your regression coefficients are what make this mean squared error small, and you can treat that, and this is really what you're doing anytime you do linear regression, you can treat that like any other optimization problem. And the basic approach to any optimization problem like this is you take derivatives with respect to all your variables. And here we're optimizing, we're moving the coefficients around. That's what we get to choose to optimize. We're going to look at all the derivatives of this loss function. And we're going to do what's essentially standard multivariate calculus on it. And we want to find the minimizing theta j, theta I. And that's in practice, that's exactly what you do when you compute those formulas. But it's important here that you could do things a slightly different way. And the gradient we're going to talk about in a minute is just the data of all these derivatives that they're essentially telling me, going back to my earlier discussion, they're essentially telling me how to make my model better. So a derivative with respect to theta 0 says, if you make theta 0 a little bigger, your model is going to get better or worse. If you make it a little smaller, your model is going to get better or worse. This is how much better or worse it's going to get. So that's statistics review. Why is this important? People have maybe heard of gradient descent. This is what this optimization approach I've been talking about is called. You get into many fancy refinements you might hear about if you're interested in deep neural nets, stochastic gradient descent. You can do regression like this. People don't normally because they have this nice formula, but you can do regression like this. And after you go through all the formulas, basically what you do is you have some coefficients. And going back to my kind of very high level schema, how does federated learning work? The modeler is going to send all the people with the data some guesses at the coefficients. There's an update rule. Based on the data, you get new coefficients. And then I have a new better guess at what my coefficients should be. And it happens to turn out that that computation of computing the update rule is something I can break into pieces over all the different people that hold data. So if I'm Gunther, I'm going to say to all these different healthcare entities, the Greater Isle of Man Radiology Association, I'm essentially going to send them, here's my guess at the coefficients, and they're going to compute their part of this update rule and send it back to me. And then I can reconstruct that information, add it all together, collate it as appropriate. I have now discovered how to update my coefficients to get better ones. So here we're essentially passing around information about this gradient, doing this optimization problem. And then the last layer is, well, maybe I could protect the gradient a little more. And I'm going to use one of those tools I mentioned. Sometimes it's differential privacy. Sometimes it's homomorphic encryption. If these words are not familiar to you, don't worry about it. We may or may not get to it in a minute. But they're avant-garde privacy tricks that are going to keep the data private, but still let me do just enough necessary work on it. So this was a heavy couple slides. How do people feel? Does anybody have any questions? It's a standard, it's really a standard optimization problem to do linear regression. We don't normally do it that way, but we could. And that way is very fertile ground for training a regression model in a decentralized way and a private way. And you can read 100 papers of different refinements of people doing this. And roughly this way. Oh, also, if anybody's like beauty of math kind of person, if you go all the way through unpacking this, it actually turns out to be exactly the same update rule for both linear and logistic regression, which I think is pretty cool and weird. And very convenient if you're writing software to do this, because then you only have to write it once. Okay, questions. Do people feel like they got, does anybody want to hazard a guess? What was the kind of big idea of these past two slides? It's fine if you don't remember every formula. What's the point here? Don't all shout at me at once. All right, well, maybe we can come back to it. Okay, so some notable software tools in this area. My company maintains a software development kit called Ghost PII. It's good for basic data manipulations and stuff like classical statistics and trees. There's a tool called NVFlare maintained by NVIDIA. it's worth noting, I think it's unusually true. It's always true that I think deep neural nets is kind of a separate field a little bit by itself. This is especially true for very technical reasons in federated learning. So NVFlare is very much focused on doing this kind of stuff for neural nets, and it's built on top of Torch. There's a project called OpenMind, which is a sort of really more of a community, and then they maintain pointers to a number of open source projects. A good and a bad thing about OpenMind is that there's a lot there. They can give you pointers. I think they're kind of drifting into trying to sell training. I don't know what the status of that is, I'm sorry, but there's a lot there. Some of the projects they have on their page, I think, are not in really good condition. So they're not doing real great curation. But if you just kind of want to shop around for things to poke at, that's a great place to go. And then a big bank in China maintains a software library called Fate AI, which is essentially the kitchen sink of every familiar algorithm. They have an implementation of some pretty good, more or less state-of-the-art federated learning implementation of it. Excuse me. And they also have message systems, and you can stand up a Docker container to provide some backend utility you need and things like this. It should be noted, I think, especially because of this dichotomy where deep neural nets is like a different universe than everything else. Some of these libraries are going to give you an interface like in scikit-learn that's directly for modeling, where you essentially say, here's my data. Here are some choices I made about how I want you to model. Give me the model. So Fate AI is very much in that vein. You give the interface your data, and it's going to give you back a model after doing a lot of fancy communication over a network if you've set it up correctly. And others are going to provide a toolbox to help you do an implementation. So these kind of privacy techniques I mentioned are not really easy to implement, and then maybe they're harder to implement actually than the federated learning itself. So that's probably not something you want to do. I would say this NVFlare thing is a good example of, you don't just give it your data. There's no presumed model. It's like in Torch, where you have to give it a lot of information about, this is what I want the topology of the network to be and what the update rule to be like, etc. But it's going to do a lot of this stuff like providing you with homomorphic encryption tools and managing specialized data objects built on top of these things. And in general, do a lot of backend headache stuff that is really not federated learning. And if you're doing this, especially in kind of a business setting and not as a hobbyist, you're going to be really glad to have out of your way and not slowing you down. Does anybody have any questions right here? Ooh, we do have a question. Can you share software web links? Yeah, sure. I'll just dig them up and put them in the meetup event page after the talk. And I think every one of these, if you just Google it, it's going to be the first hit. These are not, actually, my own offering here is the closest to being some weird secret that Google won't find. But I'm happy to share the links right after the chat. Anybody else? Any questions? I guess I should also add, this is an edgy space. It's kind of just been in the past few years that there's tools in a can for doing this. New stuff is coming out. A lot of companies like mine have formed in the past few years. There's a lot of active academic research. This is good and bad. So if you really like this stuff, there's plenty of it out there to play around with.
I have one question. In terms of, there are like the government regulation in data privacy, like for example, UK have UK Data Protection Act. So how this technology can enable to make sure that we are following these guidelines and things like that.
Yeah, that's here. So I will get to it.
Okay, we'll discuss
in a couple slides if that's
we can
okay.
discuss. Okay.
Where was I? All right. Yeah, so let me try to keep the show on the road, since there's slides later in the talk that people have expressed explicit interest in. Federated learning is going to be slower and more computationally expensive. All these algorithms we're trying to train in a federated way. If it was faster, we would have been doing that all along. You get a lot of parallelization for free, so sometimes it's not that bad. I can't make a real honest blanket statement about how much the cost is going to be, because there's different ways of doing this. So I want to point out a few things instead about why it is slower and what are some of the pros and cons about how you design this kind of thing. So an obvious-ish one and important is you pick up network latency, and there's very little you can do about this. In practice, we're doing federated learning. We have all these different actors. We're sending data around to train a model. Basically, Gunther's modeling shop would be hitting a bunch of APIs to get information back. And depending on how good the engineers built those APIs, you could pick up 1/10 of a second, 1/2 of a second every time. If you have to do 10,000 training cycles, whatever that latency is times 10,000 is maybe a while. And that's, of course, something you can do a lot of prosaic engineering work to improve, but there's always going to be a story of now part of your runtime is network latency, and there's no way of just kind of totally getting that out of the picture. Okay, so second, I talked about, you could do this multiple regression by gradient descent kind of thing. So we're having all these gradients flying around. One gradient is not going to give away the data. That's pretty safe. If you're doing a lot of gradients, maybe you can do some kind of linear algebra and do an attack and steal the data. So people do federated learning with just that gradient. They sometimes do a couple other privacy tricks on top of that gradient to protect it even more. It depends on your risk sensitivity and computational resources, and probably, unfortunately, whether you really know what you're doing or not. So whatever kind of privacy tricks you layer on top, these are also expensive. And those can be major factors in added runtime. And then finally, the fastest way, if you're just sitting at your laptop tinkering in scikit-learn to get your regression coefficients, is the direct computation. It just crunches a bunch of formulas based on your data and you're done. We talked about you could get your regression coefficients by this iterative gradient descent-based method. That could also turn out to be considerably slower. So you make some choices about how everything that's set up, and you're going to pick up a lot, potentially, or a little bit, sometimes a lot of extra runtime for these kinds of reasons. And you got to be prepared for that, and you got to know it's a kind of cost benefit of how much time do we have, how important is that, how important is privacy, and this kind of thing. Is that okay with everybody? So really, just long story short, unfortunately it's slower, and it's kind of complicated, the story of how it's slower. Okay, business value. Why do you do this? Cybersecurity, this is kind of an obvious one. An attacker breaks into your system and they see a bunch of strangely encrypted gradients. Does your average cyber attacker know what that is? And do they have the ability to do anything with it? Your average nation state signals intelligence group probably does, but your average teenage criminal in Macedonia, I don't want to pick on Macedonia, that's not fair, but like in cybersecurity, there's the term script kiddies. Your average script kiddie absolutely does not. So potentially you could get cyber attacked, and they could get in and look at what you're doing with this federated learning and just say, I'm never going to do anything with that data, I give up. And that would be great for you and could spare you a lot of pain and legal liability. Compliance, I'll talk about this again in just a second on another slide. I'm not a privacy lawyer and I'm a little out of date, but it tends to be true. And it was certainly true of the European Union 2 weeks ago. The guidance was that, well, you're not supposed to send data to the United States because the asshole US government is going to spy on you, and that's illegal here. But if you can keep the data obscured via encryption or tokenization or some kind of technique like this, it's okay. This is not caught on yet, but I'll shout at you now that it should, in that you can use this kind of technology to, if you needed to have something go to the United States, you can use this kind of technology to comply with the law and still do whatever it was you were doing. And this is actually much more general in federated learning, as we'll talk about on a following slide. There's a lot of great compliance potential here, especially in situations where data is crossing international borders. And when you do find a privacy lawyer, I'm sure they will tell you there's a ton of flux around what the rules are. This is a great way to future-proof yourself. Okay, the subtlest good reason to do this, in my opinion, is business development. It happens all the time. People are trying to do some kind of data project, and especially in an era with scary regulated data like healthcare, they get squeamish about sharing the data. Not just like things that you started doing and you kind of got into a quagmire if you couldn't agree, but there's a lot of things people don't do because they don't know that it's possible to solve these problems. So I personally really think, kind of oddly, the power of this kind of approach is in business development and in convincing people to undertake projects that they would have been too squeamish to undertake otherwise because of fear of the risk of compliance and cybersecurity concerns. And I'm guessing in 20 years, it's going to turn out that was really what the power of all this kind of high-tech stuff was. Okay, so to get the question explicitly, I want to talk really quick about what these methods are. So has anybody heard of homomorphic encryption before? Okay, so homomorphic encryption, I'm sorry I've said the word a zillion times and not yet defined it. Also, sorry I'm getting confused. There we go. Okay. The idea of homomorphic encryption, you've heard of encrypted data at rest. This is encrypted data in use. And the idea here is that I could encrypt two numbers and give them to you. You can't see what they are. You have a special algorithm called addition. You're going to take the two encrypted numbers I gave you, which are maybe literally like weird strings of letters and things, and you're going to put them into this addition function, and you're going to get new nonsense out at the end. And the trick is that you can send that new nonsense back to me, and I decrypt it, and you got the right answer. You didn't know what the right answer was. You didn't know that you added 5 and 7 and got 12. But I knew the numbers were 5 and 7, and I didn't feel like adding them together because I'm really lazy for some reason. I sent them to you, and you did that work for me. Thank you. Now that I know that their sum is 12. I hope it is fairly clear the value of this kind of thing in federated learning, where we are sending these bits of data around. We're sending them to Gunther's AI consulting in the middle to build a model. We don't want Gunther to figure anything out about us. We want Gunther to do work for us and give us a model at the end. Okay, sorry. So back to regulation. This is actually much more general, this idea. And I'm sorry, I'm a little behind on UK law. I would have loved to talk about UK law, but I'm not a privacy lawyer. But I believe it's still fairly close to Europe. And then also Europe has been in turmoil the past couple of weeks. So if this is slightly out of date, I'm sorry. But if you wanted to send data into an application that was hosted in the United States, recently that's been illegal if that's data about European nationals. Because once again, the asshole US government is going to spy on you, and how are you going to stop them? You can use a technique like homomorphic encryption, exactly as I described it on the last slide. You encrypt the data first, and you keep the keys in Europe, or you keep the keys in the United Kingdom, or in China, or wherever it is that people don't want to get spied on by Americans. And then you can send that to that server in America, and it's going to be handled while it's encrypted. And even that server handling the data doesn't know what the data is, but it's going to do whatever the thing is that it is supposed to do. It's going to add up a bunch of numbers and give you an average, or it's going to look up what row is the primary key, like the foreign key 10,000 in. Give me everything in that row, or whatever it happens to be. It can do that work. It's going to send that back to you encrypted, and then you decrypt it. So plain text is going to live only in Europe. And in the United States, there will only be ciphertext. And in addition to protecting your privacy, which is great, this is now legal. It was illegal before under European law because of failure to protect against surveillance. Does that answer your question, by the way?
Yeah, of course. Yeah. Let's get it.
Okay, great. I have 2 minutes left. Has anybody heard of differential privacy? Okay, I have another talk I'm willing to give. I'll come back if you like this one. I'll talk about differential privacy. Because I have an axe to grind, this always comes across as way fancier than it is. Differential privacy in practice is, if you have a dense data set with a lot of similar people in it, it works really well from a theoretical standpoint to just add noise to it. Just add noise to the data. So here's an example. I took my real life information, height and weight and age, and then I generated randomly a bunch of fake people similar to me. And then I did very basic differential privacy on it. I added more noise to everybody. And the game is, which of these is me? And so it turns out that the row that's closest to my real data isn't the one that kind of started out as my data. It's somebody else's data that got a little bit of noise added to it. And so this is important because, well, what if at the end with this data is like, I've got an embarrassing disease. Pick your favorite embarrassing disease and you don't have to tell me. Maybe you might triangulate me in this data by my height, my weight, location. You add this little bit of noise, I can be like, nah, it's not me. I don't have that diagnosis. You're confused. I'm this guy over here who's in great health and just has like ripped 6-pack abs and everything's great about him. And there's really no way to say that I'm fibbing. So this is another very powerful technique. It comes up in federated learning a lot. If you read the Wikipedia page, and this is my axe that I'm grinding, the Wikipedia page makes this sound like awful rocket science. And there is some rocket science out there. If you do this in the wild, you're probably adding noise to the data according to some recipe in some academic paper. And the academic paper maybe did something fancy to know what that noise should be. On the implementation level, you're just adding, hey, give me some Laplace noise with the following mean. It's not as bad as the Wikipedia page makes it look. And I wasn't joking. I'll come back and give another talk. I'm out preaching the gospel here. Okay. That's all she wrote. I believe we're at the hour. If you liked anything you heard, you've got these slides. The slides have my email, Twitter, LinkedIn. I'm especially active on LinkedIn. I shout about this stuff all day, every day. I'd love to hear from you if this stuff appeals to you.
If you have any questions, you can ask.
Don't be shy.
Seems like no questions at the moment. They will contact us via email and they can reach us the meetup page as well. Okay, so then thank you all for joining the April AI meetup. Right, thank you for feedback, Alex. So thank you for joining the April monthly meetup, and thank you, Alexander, for sharing this knowledge about the federated learning. We learned a lot about the federated learning, and we hope to see you again in our meetup group as well. And if you have any questions, you can further reach out to us with the email addresses. And also, we'll be sharing the recording of the this meetup also in few days of time, so everyone can take a look at it. And any other further questions you can have, you can reach out to us. Thank you all for joining to the meetup, and we're looking forward to seeing you again. Yes, Alex. Yeah.
Thanks for having me. I appreciate the opportunity to speak.
Of course. Yeah, mostly welcome. Yeah, of course. Thank you, everyone. Have a nice week.
Bye-bye.